I'm going to share about how Swift deals with modules, and particularly get into some more details about our module loading strategy. To start with, Swift is a modern language, and as such, it was designed to be modular from the start. And modules in Swift are very much a core vertical concept that spans encapsulating a collection of source files that contributes to a given library, the ABI contract that it provides to its clients, the API surface that a given library represents, mapping down all the way to the symbols we capture in the resulting binary file. And unlike the C family of languages, in Swift, module interfaces are not authored by a human in a textual header file. Instead, they are captured directly from your source code by using access control keywords. So the public keyword in this example comprises the full set of declarations and types and functions that will contribute to an interface of your module. And once you have a module, in order for your clients to be able to actually use it and reference all of those declarations and types, it needs to be compiled into a binary representation ingestible by the compiler, which is a binary Swift module, which is an LVM bitcode container that captures the abstract syntax tree of all of the relevant declarations. And as of Swift 5 on Apple platforms, we also have a compilation mode where users can opt in to build a resilient module, which provides a guarantee of ABI stability. So as your library evolves over time and you make your additive changes, your modules are stable in that your new versions will be compatible with the clients built against your prior versions. And to do that, we also need to produce modules that are not tied to a given compiler version and are usable across different compilers. And so to do so, instead of a binary module file, the compiler will produce a textual module interface, which works very much similarly to the binary file. It uses the access control mechanism to capture all of the relevant declarations. Now, crucially, since day one, Swift has had a deep interoperability with C and ObjectiveC code, and as of recent as well with C++ code. And there is a mechanism in Swift to simply import a given textual header file and all of the various mechanisms in it. But in order to do interoperability at scale, if you want to ship a large mixed language SDK, for example, requires modularized header interfaces. And as we've all learned earlier, we use the mechanism of Clang modules for this. Clang modules are composed of a module map file that defines a module name, crucially, as well as all of the various properties of this module and the header files that comprise it. And Clang modules are built into binary pre-compiled module files. So all of the possible ways that Swift can import modules, we can learn them by looking at a small example. So suppose we're compiling a small Swift program consisting of a source file that imports modules foo and bar. Suppose module foo is a resilient Swift module somewhere on the search paths of our compilation, and bar is a Clang module. Upon encountering an import statement, the Swift compiler is going to discover that we have a textual interface for this module. This module needs to be built into a format ingestible by the compiler and then consumed into the main source compiler, which can then proceed to the next statement. Similarly for bar, we can discover this module. We have this precompiled module representation of it. There's an additional step we need to go through for Clang modules called the Clang importer, which is a subsystem of the Swift compiler that essentially goes over the full list of declarations in this Clang module and translates them into the format that is native to the Swift AST in order to be able to directly use those declarations. The key concept here is that each named module requires to be compiled into a format that the compiler can actually ingest. And so if we take a step back and look at compiling a more meaningfully interesting piece of source code where you're building a Swift target that consists of many different source files, each one has its own import statements, this process looks something like this. Swift compilation model defines the module itself as a compilation unit. But similarly to Rust, as we saw in the keynote yesterday, for debug builds, we actually separate a module into per source file compilation tasks in order to make better use of the many cores on our machines. And if you're building a library that is meant to be consumed by clients, we're going to have a separate task that also emits the module itself. Looking at this example, once we encounter an import statement, the compiler needs to search the file system in a given set of search paths. Do I have this module? And suppose one of the tasks here encounters an import of foo, and what it's going to do is it's going to spawn a compilation subinstance. It is going to take its own compiler process, take a certain subset of the compilation context of all of the flags, the target triples, the -d flags, and spawn a new thread to go and compile that module. And it can't necessarily make any forward progress until that compilation thread is done. Now, it is very likely that within the same module, you're going to have a different source file that has exactly the same module dependency. And if when some other source file encounters an import of foo, we don't really want it to also spawn a thread to go and build the same module. We don't want to duplicate that work. And so we are simply going to place a file system lock on that module and have this process wait for it. And also notably not be able to make any forward progress because it too needs the contents of foo. And so all this process is going to do is simply spin on that file system lock and wait. Now, this process sort of goes on and on and on. Emit module tasks will require all of your modular dependencies. They end up doing a lot of waiting. Eventually, some other source file compiler is going to encounter an import of bar. It's going to start a compilation. Other tasks are going to start depending on it. All of this gets very complicated very quickly. And if you think that's a bit much, things get really interesting when we remember that foo and bar are themselves modules. They also have modular header includes. They also have import statements if they are themselves Swift modules. And how we handle that is actually exactly the same. When we're compiling foo, we encounter import statements in its textual interface. That compilation instance is going to spawn its own sub-compilation instance thread, which is going to place a file system lock that some other process somewhere else is going to end up waiting on, and so on and so forth. And just anecdotally, when you're building any kind of meaningfully sized Swift program like against the macOS or iOS SDK on Apple platforms, it is fairly common to have a given compile have a module dependency graph that consists of in the order of hundreds of both Swift and Clang modules from across the SDK. Now, this process, it works well. It has served us for many years, though over the course of our experiences with it, we've found some downsides to it, as well as found that it doesn't necessarily scale to the kind of build system technologies we want to build. And to highlight some of the downsides, in addition to the various correctness pitfalls that Michael and Ian highlighted, is that this process is entirely opaque to the build system. When a build system creates a set of tasks to compile a given target, it doesn't have any idea of how much work a given task is going to take, how many threads it's going to spawn, how to best take advantage of your machine's resources. Peer tasks end up waiting on these file system locks, making no forward progress, but also at the same time taking up valuable execution lanes, which is clearly suboptimal. File system locking mechanisms are brittle. You need to be really, really careful when your process halts for some reason or you encounter some kind of errors. Nested compilation context is hard to reason about. This does end up translating into fairly difficult errors for our users to debug, but notably it's also particularly tricky for compiler engineers to debug. Whenever something goes wrong when you're compiling an SDK dependency module that is dozens of threads deep into a compilation, threading the needle through that compilation of what exactly went wrong and in which order can be very tricky. Notably, these tasks are non-isolated. And what that means when we spawn these tasks, neither the build system nor the compiler actually know what files are going to be used as inputs to this compilation task, what files are going to be produced by this compilation tasks, which can be a useful property to have. Last but not least, we get very late error discovery. A lot of things need to happen in a compilation process. We again may need to follow these sub-compilation threads that are dozens and dozens of contexts deep in order to finally hit a cycle, at which point, in order to produce meaningful diagnostics to our users, we need to do a lot of work to reconstruct all of the chain of events that led us there. And so the solution to this is a model we call explicit modules. I'll refer you to, once again, to an excellent talk my colleague Jan gave at EuroLVM in 2022, where he described how a similar model is applied to Clang. And here I'd like to highlight how Swift is doing something similar by building on top of the work done in Clang and using the infrastructure that Clang built for explicit modules directly. The key concept of explicit modules and the new model is that we break up the build into 3 stages. In the first stage, before we perform any kind of compilation, we're going to perform a dependency scan. So we're going to find all of the import statements in your Swift code. We're going to resolve them to their modular dependencies. We're going to follow those links, resolve the modular dependencies transitively, and so on and so forth. And the end result is this dependency graph. And the graph consists of, for every module, here's what it is, here's the files that comprise it, and here's a full command line recipe that you need to build it. Once we have that, the compiler driver or whatever build system is orchestrating this can schedule these modules to be built in dependency order. And finally, we build our source files. And crucially, these source file compilation tasks now will not spawn any new threads. They will not themselves wait for anything. All of the inputs are specified directly and explicitly. And crucially, if you're not building that many source files, or in the Swift compilation model, if we're building an entire module in a whole module optimization flow, you're just going to have one compile tasks, and you are still going to be able to use the many cores that you have on your machine when you're building your dependencies, which we can hopefully do a much better job scheduling. So we can compare the two approaches, whereas previously we had these collection of long-running tasks that are fairly inscrutable, both to us and to our users. We now ultimately have a much more coherent kind of task graph. And to highlight some of its advantages is we've unlocked a lot more scheduling parallelism opportunities. As I mentioned, our dependency graphs can span in the order of hundreds of modules. Our machines are getting more and more cores. We can make much better use of it because we have much more parallel work that we've discovered up front. Our compilation tasks are isolated. All of their inputs and outputs are precisely specified ahead of time, which can be a very useful property, particularly if we want to do something like make them eventually distributable. We have greatly simplified the debugging of this. And crucially, this isn't just the debugging by compiler engineers who are looking at this, who can now look at a given task, have much more precision knowing what this task was doing and what could have possibly gone wrong. But also the many users who at their desk may encounter various issues that involve modularization. Also for our build engineers who are oftentimes triaging various modularization issues when building our SDKs and ensuring their health. Being able to have an upfront dependency graph as well as a precise attribution of failures is extremely valuable. Last but not least, this process is now deterministic and explainable. We are no longer bound by waiting for which specific source file encountered a given import statement first and started its compilation, which will or will not necessarily happen on sort of successive compiles of the same thing. We now have a much clearer picture of the compilation model. Now, the most interesting technology involved in this build model is the dependency scanner. The Swift dependency scanner is a library service that is used by the build system. It essentially is a library that wraps the entire compiler, whose execution mode is strictly to take an import statement and to resolve it to a given module in a file system. And because Swift directly interoperates with Clang modules, the Swift dependency scanner actually fully wraps the Clang dependency scanner. One of the great advantages of this system is that Swift source code does not need to distinguish when importing a module, whether that module is written in Swift or in Clang. It's all quite transparent. The dependency scanning service itself consists of a collection of workers. When you have many different import statements to resolve, we can attempt to do those in parallel. And the pseudocode for this is actually really straightforward. We start with a collection of source files, each one with its own collection of import statements. For each import statements identifier, we ask a question of, does my collection of search paths have this module in a file system? If it does, that's great. We go and find that Swift module, we take its imports and add them to the work list. If we don't, we now query our built-in Clang dependency scanner. And the Clang dependency scanner needs to work quite differently. It cannot simply give us a single module and its dependencies. It needs to give us a full subgraph of dependencies of the module we're querying. And the reason for that is because the sort of dependency set and the interface of a Clang module you're importing can actually be affected by its dependencies in turn. So we need to get the entire subgraph from the Clang dependency scanner. And if the answer to the second question is also no, we know that we don't have any such module, and we can tell the user, please check your search paths. The API that the Swift dependency scanner uses for this is actually really straightforward. The Clang dependency, Clang modules are named. The module identifier is specified in a module map. So we query the scanner with this API called getModuleDependencies that takes a module name. A command line definition that defines the compilation context that is looking for this module and therefore defines the context hash of this module that contains the target triple, all of its macro definitions, et cetera, et cetera. Now, one of the key lessons that we've learned in transitioning our compilation model to use explicitly built modules is that dependency scanner performance is crucial. We have unlocked a lot more parallelism by having a much richer upfront task graph of all of the module dependencies. But if you remember those little timeline slides, to unlock that parallelism, you do need to run this bottleneck task that first needs to compute this graph. And as we've spent some time studying performance characteristics of this process, we've discovered that, well, Swift module discovery is relatively very, very cheap. And the reasons for that are, one is Swift is a fully modular language from the get-go, and it's also more restrictive in the kinds of things that module interfaces can express. For example, modules on the file system, Swift modules on the file systems are named after the module name, whereas Clang modules are all, in order to find the identifier, you first need to find every single module map that appears on your search paths, open one, parse them all, find the right identifier, go parse its headers and pre-process its headers, which ends up being much, much more expensive. And also, as I mentioned, to compute what the recipe for building a given Clang module dependency, you need to compute its entire transitive closure graph. And so one insight that we've pursued recently is that relying on the fact that a Clang module cannot actually have a dependency on a Swift module, we can compute the full Swift module dependency graph ahead of time, and everything that is left unresolved has to be Clang modules, which we can then try to resolve as one large batch. And what that process looks like now is that, just as before, we start with your collection of source files. They have a collection of import statements with just named identifiers. We resolve all of those to Swift modules. Again, takes reasonably insignificant amount of time. And then we know that every single unresolved node in this graph must be a Clang module. We can grab those, put them in one large batch of queries we dispatch to the Clang dependency scanner, and issue those in parallel. And that's Swift explicitly built modules. Thank you for listening. I'll be happy to take questions.
Do we have any questions?
Nelson Amaral, University of Alberta. I assume that you rebuilt the dependence graph from when there is a modification for recompilation, not from scratch?
No.
Oh.
No, not from scratch.
So the question then is, what are the difficulties on partially rebuilding the dependence graph, given that you have this separation with the Clang modules?
We don't do a partial recomputation of the graph, but the way this works is that the Clang dependency scanner, as it computes subsets of a dependency graph, it serializes the graph state. And so on an incremental build, when we launch a dependency scanning process, whenever the scanner encounters a query for, oh, I'm compiling a source file that needs to find foo given a certain command line invocation, the scanner is able to reuse the previously computed work. And so we do not recompute slices of the graph. We incrementally recompute the entire graph, but we don't need to do much of the work. We simply need to have mechanisms in place that do all of the required consistency checking. Is my serialized stuff up to date? Did this module dependency changed? And if it hasn't, we are able to reuse it. And if it has, we need to invalidate that node and do a from scratch query. So there is this incremental machinery that takes the entire graph and then validates sections of it that need to be recomputed incrementally.
Does anyone have any other questions? We have time. All right, thank you, everyone. Let's thank our speaker for his talk.